Welcome back to the energy conversion lectures. In many applications, such as electrical machines and transformers, the voltages and the magnetic field vary sinusoidally with the time. To elaborate on this relationship, let's consider the following magnetic circuit. If the coil is fed by an AC source, a current I will flow and establish a magnetic field phi and back EMF voltage E. Now let's assume that the voltage applied at the terminal is sinusoidal and equal to V equal E equal EM sine omega t, where EM represents the peak or maximum value of the instantaneous voltage V, omega represents the angular velocity, and it is equal to 2 pi f, where f is the operating frequency. As we have learned from previous lectures, Faraday's law represents an important relationship between the magnetic field and the induced voltage. Therefore, let's apply Faraday's law in order to understand the nature of the magnetic field phi waveform. Now, by applying Faraday's law, the magnetic field phi can be identified by integrating the induced voltage as follows. As you can see, the magnetic field phi is also sinusoidal and lags the induced voltage E by 90 degrees. The maximum value phi m of the magnetic field phi is equal to phi m equal Em over 2 pi Fn. If we rearrange this formula, the maximum and RMS value of the induced voltage can be calculated as follows. Em equal to 2 pi Fn phi m, and the RMS value ERMS equal to Em over root square 2, and this will equal to 4.443 multiplied by n multiplied by f multiplied by phi m. This is a very well-known relationship between the voltage and the magnetic field, and we need to always memorize it. At this point, we have identified the nature and the relationship of the magnetic field and the induced voltage of the magnetic circuit. In other words, we confirmed both the magnetic field and the induced voltage are changing sinusoidally with the time. So now we need to study and understand the nature of the excitation current waveform that produces the magnetic field. To do that, graphical method will be used. 3 cases will be covered based on different BH curves. The first case is linear BH curve. The second case is nonlinear BH curve with hysteresis ignored. And the last case is nonlinear BH curve with the consideration of the hysteresis loss. Before I start with the first case, I would like to mention here that the BH curve of the magnetic core can also be represented by phi I curve because magnetic field density B is function to the magnetic field phi, and the magnetic field excitation H is function to the excitation current I. So now let's start identifying the nature of the excitation current for the linear phi I curve case. We proved earlier that the magnetic field is sinusoidal and lagging the voltage by 90 degrees. From these 2 curves, we can graphically plot the excitation current by taking some points from the magnetic field phi waveform and map them on the phi I curve to find the corresponding current points of the excitation current as shown. For example, if we map point 2 on the magnetic field phi on the phi I curve, the corresponding point of the excitation current can be identified. Now, if we rotate the resultant current waveform 90 degrees, we can see that the excitation current I phi is sinusoidal. Also, the current and the magnetic field are in phase. It is obvious now that when the BH curve is linear, or the magnetic circuit working within linear region, the excitation current is also sinusoidal and has no harmonics. In other words, the current required to produce the linear BH curve has no harmonic and is changing sinusoidally. The equivalent circuit and vector diagram of such case are as follows. Now let's repeat same exercise, but this time assume that the BH curve is nonlinear and the hysteresis loss is ignored. As you can see, the current required to produce such non-sinusoidal BH curve will be non-sinusoidal as well. Now, if we rotate the resultant current waveform, we can notice that this nonlinear current is in phase with the magnetic field and out of phase with the voltage. If we analyze this non-sinusoidal current waveform and determine its spectrum components using Fourier analysis, we can determine the fundamental component of this non-sinusoidal current as follows. The equivalent electrical circuit and vector diagram of this nonlinear I phi curve can be represented as shown. As you can see from the vector diagram, the fundamental component of the magnetic field is lagging the voltage by 90 degrees. Now let's cover the last case where the core I phi curve is non-sinusoidal and the hysteresis loss is considered. This I phi curve represents a real magnetic core characteristics. As you can see, the current required to produce such I phi curve will be non-sinusoidal and has more harmonics comparing with the previous case. To have bigger picture, let's plot the resultant current waveform together with the magnetic field waveforms as shown. One interesting point here is that there is some current drawn by the magnetic circuit while no magnetic field is produced. This current simply represents the current drawn because of the hysteresis loss. The other interesting point is that there is some residual magnetic field while the current I phi is 0. Basically, this resultant current I phi represents an instantaneous sum of two components, the magnetizing current Im, represented by purple color, and hysteresis loss current IC, represented by red color. The current IC is accounting for the hysteresis power loss, and the current Im is accounting for the magnetization current of the core. The magnetization current Im is the same as the excitation current if the hysteresis loss is ignored, which explained in case B. This phasor diagram shows the relationship between the voltage, the current IC, the current Im, and the current I phi. Now, since the current IC that represents the loss is in phase with the voltage, the equivalent circuit of this part can be modeled as resistance RC. Also, since the current Im is lagging the voltage by 90 degrees, the equivalent circuit of this part can be modeled as inductance. Therefore, the total equivalent circuit that represents nonlinear BH curve with hysteresis loss is basically a resistance in parallel with inductance as shown. Let's conclude this lecture at this point. Thanks for listening. I am Ihsan Al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.